Section 13.2 Chemical Equilibrium. In earlier chapters, we considered the forward reaction in an equation and assumed that all of the reactants were converted to products. However, most of the time, reactants are not completely converted to products because a reverse reaction takes place in which the products collide to form the reactants. When a reaction proceeds in both a forward and reverse direction, it's said to be reversible. We've looked at other reversible processes. For example, the melting of solids to form liquids and the freezing of liquids to solids is a reversible physical change. Even in our daily life, we have reversible events. We go from home to school and return from school to home. We go up an escalator and come back down. We put our money in a bank account and we take the money out. An analogy for a forward and reverse reaction can be found in the phrase, "We are going to the grocery store." Although we mention our trip in one direction, we know that we will also return home from the store. Because our trip has a both forward and reverse direction, we can say the trip is reversible. It's not very likely that we would stay at the store forever. A trip to the grocery store can be used to illustrate another aspect of reversible reactions. Perhaps the grocery store is nearby and we usually walk. However, we can change our rate. Suppose one day we drive to the store, which increases our rate and gets us home to the store faster. Correspondingly, a car can also increase the rate at which we return home. Reversible chemical reactions. A reversible reaction proceeds in both forward and reverse direction. That means there are two reaction rates. One of the rate is the forward reaction and the other is the rate of the reverse reaction. When the molecules begin to react, the rate of the forward reaction is faster than the rate of the reverse reaction. As reactants are consumed and products accumulate, the rate of the forward reaction decreases and the rate of the reverse reaction increases. Equilibrium. Eventually, the rates of the forward and reverse reactions become equal. The reactants form at the same rate as the products form reactants. A reactant reaches chemical equilibrium when no further change takes place in the concentrations of the reactants and products, even though the two reactions continue at equal but opposite rates. Equilibrium is reached when there are no further changes in the concentration of reactants and products. At equilibrium, the rate of the forward reaction is equal to the rate of the reverse reaction. No further changes in the concentration of reactants and products, even though the two reactions continue at equal but opposite rates. Let's look at the process at the reaction of hydrogen and iodine proceeds to equilibrium. Initially, only the reactants of hydrogen and iodine are present. Soon, a few molecules of hydroiodic acid are produced by the forward reaction. With more time, additional hydroiodic molecules are produced. As the concentration of HI increases, more HI molecules collide and react in the reverse direction. The forward reaction is hydrogen plus iodine yields 2HI. Reverse reaction is 2HI breaks apart into hydrogen and iodine. So the concentration of the reactants change over time and eventually reach an equilibrium point. Initially, the reaction flask contains only reactants of white hydrogen and purple iodine. The forward reaction between hydrogen and iodine begins to produce hydroiodic acid. As the reaction proceeds, there are fewer molecules of hydrogen and iodine and more molecules of HI, which increases the rate of reverse reaction. At equilibrium, the concentrations of reactants of hydrogen and iodine and the product are constant. The reactant continues with the rate of forward reaction equaling the rate of the reverse reaction. As HI product builds up, the rate of the reverse reaction increases while the rate of the forward reaction decreases. Eventually, the rates become equal, which means the reaction has reached equilibrium. Even though the concentrations remain constant at equilibrium, the forward and reverse reactions continue to occur. The forward and reverse reactions are usually shown together in a single equation using a double arrow, a reversible reaction and two opposing reactions that occur at the same time. We can set up a reaction starting with only reactants or with only products. Let's look at the initial reactions of each, the forward and reverse reactions, and the equilibrium mixture that forms. 2 sulfur dioxide plus oxygen yields 2 sulfur trioxide. If we start with only the reactants, sulfur dioxide and oxygen, in the container, the reaction to form sulfur trioxide takes place until the equilibrium is reached. However, if we start with only the product sulfur trioxide in the container, the reaction to form sulfur dioxide and oxygen takes place until equilibrium is reached. In both containers, the equilibrium mixture contains the same concentrations of sulfur dioxide, oxygen, and sulfur trioxide.